Welcome to the Lab2PreLab. In this lab, we're going to be using some calculus to analyze situations in rocket science, and we're going to see along the way that, as in the previous lab, sums and integrals are very closely related, and in practice, they can be used interchangeably. In particular, we're going to make some special use of the integral of natural log to help us analyze a situation in rocket propulsion. So since rockets themselves are pretty complex, we're going to instead model things with a simpler scenario. The main idea is that a rocket is propelled as a consequence of Newton's third law. It shoots out particles and pushes the rocket in the other direction. In our example, we're going to take a person, in this case, Phillies pitcher Robin Roberts, who is the only Spartan to ever be inducted into the Baseball Hall of Fame, and we're going to put him on ice skates. This will mimic the frictionlessness of a rocket in space. So we're going to give him some baseballs as fuel particles. He's going to throw those baseballs, those fuel particles, and slide in the other direction, right? The baseballs will go one way, and he will go sliding the other way. So it's not quite a rocket, but it has the same characteristics. Now, our goal is going to be to consider how fuel is able to give the rocket speed. In our case, how does throwing baseballs change the speed that the pitcher slides with? So we're going to use some information about our system. We're going to use 5 things. The number of baseballs he's given before the pitch, the starting velocity he has before the pitch, the mass of each baseball, which we're going to assume is 145 grams, the speed of his fastball, which is 40 meters per second, and the mass of Roberts. We're going to say that was about 86 kilograms. So if we use delta V to represent the change in velocity after one baseball is thrown, we can get a kind of crazy long equation for it right here. So delta V is the change in velocity, and that's equal to the mass of one baseball times the velocity that the baseball was thrown at. And then on the denominator here is the mass of everything left. This is everything left after throwing one baseball. So that includes Roberts, as well as all of the remaining baseballs or remaining fuel, however you want to think about it. If he had n baseballs to start with, he threw 1, so there are n minus 1 baseballs remaining times the mass of each baseball. Now I encourage you at this point to stop for a second and think about what each of these values means in the case of an actual rocket rather than our baseball themed analogy. So our main goal here is to figure out, given a fixed amount of fuel or a fixed number of baseballs, what is the maximum speed that this rocket can get to? Well, let's look at a specific example. Here we're going to consider 3 baseballs and an initial velocity of 0. We use our delta V equation, just like before, and we're going to plug in all of the numbers. Now on the denominator, there are 2 baseballs left. So we use 2 baseballs. We plug this in and we get 0.0672. Now we add that to our initial velocity to get the velocity after one pitch, which is just that same velocity. Now we do it again where we're throwing the second ball, so there's only 1 ball remaining. This gives us an added velocity of 0.0673, which we add to the previous velocity to get 0.1345 as our new velocity. We do it one last time for the last baseball. There are 0 baseballs remaining on board, and this gives us an added velocity of 0.0674. The final velocity is then our previous velocity plus this, which is 0.2020 meters per second. Going back to the pre-lab, we can see what happens when we start with a more general situation with n balls. Well, we do the same thing. We take our initial velocity and add the delta V's from each successive pitch. This type of summation can be done on a computer, which will be one of the lab activities. However, for really large values of n, like what an actual rocket uses, it shoots out a huge number of particles, the computer will struggle. So we need some way to approximate this sum in a simpler manner. And just like in the last lab, we're going to link together sums and integrals. So if we have a sum where each term is represented as a function evaluated at certain points, maybe the first pitch, the second pitch, the third pitch. Those are all of our delta V's. We want to add them all together. We can think of this like a Riemann sum, where the width is just 1 always, and the height is the value of each function. Then this Riemann sum looks like the Riemann sum for the integral of the function k of x. So if we can just take the integral of k of x, this should be a good approximation for the summation here. So that's the last topic on the pre-lab. Thanks for watching, and good luck on the lab.